Year 12 and welcome to the run through of the paper 2 that you did just before half term as your end of year exam. The majority of this was taken from the 2019 paper 2, although this first question actually comes from a slightly older source. As before, you should spend this third lesson of the week looking through the mark scheme, analysing where you lost marks and why you lost marks, and perhaps identifying areas for further study. And then in the final lesson of the week, you will be asked to complete the rest of the 2019 paper 2 and submit your answers on Google Classroom, as you have done for the paper 1 answers. So without further ado, let's get started. Give the molecular formula of this alkene. So let's draw it. 1, 2, 3, 4, 5, 6, 7 carbons. In terms of hydrogens, you got 1, 2, 3, 4, 5, 6, none there, 7, 8, 9, 10, 11, 12, 13, 14, C7H14. Reject C7H14 written with superscripts. If anyone's still doing that, they really shouldn't be doing chemistry. Explain why the alkene exhibits geometric isomerism. Well, it's due to this double bond here and the fact that you don't get rotation around this double bond, and therefore there are two different molecules that you can have where these groups, the hydrogen and this ethyl group, are on opposite sides and they are different molecules. So the first mark, anything to talk about the fact that there's no free rotation around the carbon-carbon bond or around the pi bond, no rotation. It does say restricted because under UV light, for example, you can rotate, but it's restricted rotation. The second mark is for talking about there are different groups, different atoms with different masses on each of the carbon atoms of the carbon-carbon bond, or two different groups on either side of the carbon-carbon bond, or three different groups around the carbon-carbon bond. Anything saying that you had at least three different groups attached to that CC bond. Allow clear diagrams showing the two different groups or the two different isomers. But it does say reject, talking about compounds, molecules or branches attached to the carbon-carbon because they're not technically correct. And ignore just four different groups. You had to talk about them being on either side of the CC bond with the restricted rotation. Propane reacts with three different reagents. Give the reagent needed for reaction 1. Well, clearly here that carbon-carbon bond is being turned into a bromine group and an OH group. So you definitely need bromine, but the reason you can't just have bromine, Br2 or bromine liquid, is because you also are adding an OH group, and therefore you need bromine water, aqueous bromine or Br2AQ. So the bromine comes from the bromine molecule and the OH comes from the water. Identify by name or formula the organic product A formed in reaction 2. So you are adding acidified potassium manganate to an alkene, and as you should know, that will convert each of those into an OH group. So hydrogen, hydrogen, OH, hydrogen, and then the other side of that is also an OH group, carbon, hydrogen, hydrogen, hydrogen. So it asks you for the formula or the name. Well, this is clearly 1, 2, 3, propane, so propanol, because it's got the alcohols, so propan 1, 2 diol. Okay, that would be the name. In terms of formula, 1, 2, 3 carbons, C3, 1, 2, 3, 4, 5, 6, 7, 8 hydrogens, and 2 oxygens. So let's hope that that matches what you've got. Propane 1, 2 diol, or as it says there, propan 1, 2 diol. So propane 1, 2 diol, propan 1, 2 diol, both fine. 1,2 propane diol, also fine. But ignore 1,2 dipropanol, okay? So you've got to have that diol, so that was a rejection. Or you were allowed to give the structural formula there. So that's what I've drawn up there. It does say ignore the molecular formula C3H8O2. Luckily, I had done both, so I would have got that mark there. State the colour change you would see in reaction when reaction 2 is carried out. Well, you are using up the potassium manganate 7. The potassium manganate is a bright purple colour in high concentrations, pink when it's in lower colour, and as it's used up, you end up with a colourless solution. Not clear, colourless, remember that. So purple or pink to colourless. Give the mechanism for reaction 3, use curly arrows and show any relevant dipoles and lone pairs. Okay, so we're adding hydrogen bromide. So C, hydrogen, 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 carbon, hydrogen, hydrogen, hydrogen. Remember, this is electron rich here, so this is going to attract anything that's positive. And if we've got HBr, then because of electronegativities, the hydrogen is delta positive, attracted towards that. The bromine part is negatively charged, so that's going to be oriented away. So clearly the electrons from this bond are going to move towards the hydrogen, breaking that bond and pushing the electrons up onto the bromine. Now we need to think about which cation is going to be more stable. We can end up with a cation on this carbon or this carbon. And when we look at the substituents, we see that this has got 2 hydrogens attached. So these aren't very good stabilizing groups. The CH3 group here, the methyl group, is much better at donating electron density to stabilize a carbocation. So the cation is going to form on this. So that is going to form CH, hydrogen on that. Carbon, which is going to be positive, hydrogen stabilized by the methyl group here. And then you've got the bromine with the negative charge. The lone pair on that bromine is going to attack the cation. So this is going to be nucleophilic attack, something attacking a positive charge, and you will end up with CH3, CBr, hydrogen, CH. So again, to remind you what the question was, give the mechanism for reaction 3, use curly arrows and show any relevant dipoles and lone pairs. So 1 mark for showing the correct dipole on HBr. So it did even tell you to show the dipoles. So 1 mark for getting the correct dipole on HBr. Curly arrow from the double bond to the hydrogen of HBr and a curly arrow from the HBr onto the Br minus. That's what we did. The second mark there. The correct intermediate with the positive charge. So there was specifically 1 mark for showing that the cation would be on the middle carbon there. And finally, curly arrow from anywhere on the bromine, including the minus sign or the lone pair, to that carbocation. Ideally though, showing a lone pair on the bromine and the curly arrow from that to the carbocation. But it did allow it from the negative sign onto that carbon, and that was your 4th mark. So what did it not like? It didn't like half-headed arrows. Okay, remember that is the movement of 1 electron. That is radical reactions. These are not radical reactions. Ignore missing hydrogen on structures once only, so that's penalise that once. Butene polymerizes to form polybutene. Draw a section of this polymer showing 2 repeat units. This is just from GCSE, right? So remember, whenever we're drawing an addition polymer, we base it around R1, R2, R3, R4. So if we draw butene like that, it's going to be CH3, C, C, CH3. Hydrogen here, and if that polymerizes, well, as you know from GCSE, scrub that out, bond there, brackets and N, but here we're asked for a section of the polymer showing 2 repeat units, so carbon, 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 CH3, hydrogen, CH3, hydrogen, hydrogen, CH3, hydrogen, CH3, okay? And hopefully that's what you've got there, exactly. Allow CH3 groups above or below the chain, allow fully displayed formula, ignore brackets and any ends, ignore bond angles and bond lengths, ignore working. All it wanted you to do was really show that you just know how butene is going to polymerize, and checking that you know what butene is as well. Right, the question you've got is slightly different here. So the question actually on that was calculate the percentage atom economy by mass for the production of cyclohexene. The question you've had is basically identify the type of reaction and the reagent. That's what it asked for, and I think that was for 2 marks. Okay, so there's 2 things. Firstly, you could call it an elimination reaction, or you could call it a dehydration reaction. You're removing water, dehydration. So that was for the 1st mark. And the second thing you need is the reagent that's needed, and you need acid. Ideally phosphoric acid, because as we know, sulfuric acid can be an oxidizing agent, and that can lead to some unwanted side reactions. But basically this is more than you needed. The OH group is going to become protonated by the acid, and then this is actually, because it's a secondary alcohol, it's going to go via the E2 mechanism. So that's just going to leave as water, leaving you with a stabilized carbocation there. And then along comes the water molecule with its lone pair, takes that hydrogen, and the electrons from that go to form the double bond. And here you have regenerated the acid catalyst that you used in the 1st step to protonate that. Okay, that was extra information, but that's what's going on there. Now, this was back to the questions you were asked. Calculate the percentage yield if 10.2 grams of cyclohexanol produced 6.15 grams of cyclohexene. Right, first thing, how many moles of cyclohexanol do you have? Well, 10.2 grams. The formula mass is 100, so you've got 0.102 moles. It's clearly a 1-to-1 ratio, so you end up with that number of moles of the cyclohexene. The mass of cyclohexene is 82 grams, so you should make 8.364 grams of cyclohexene. So if your yield was 6.15 grams, 6.15 over 8.364 times by 100, 74%. Ignore significant figures unless you only give 1 sig fig, so don't write 70%, but anything else, provided it was correctly rounded, would have been fine. Organic compounds can be grouped together in homologous series. Describe two characteristics of a homologous series. The two that I would say is that they have the same functional group, they display similar chemical properties, allow the same chemical properties, but they show a trend in physical properties. These are the two things I hammer home to my GCSE students. Homologous series have similar chemical properties and a trend in physical properties. You could also have had, they have the same general formula, for example, CnH2n plus 2, but do not allow the same formula. That's wrong, okay? The same general formula, for example, CnH2n plus 2 for alkanes. And you could talk about neighbouring compounds differing by a CH2 group or something like that if you wanted, but these two are the most obvious to me at any rate. Propene is obviously an alkene, and propene can be converted into a mixture of 1-chloropropane and 2-chloropropane, in which 2-chloropropane is the major product. Okay, so what are you adding to this? Well, we've seen this earlier, that if we want to turn an alkene into this or similar, then the way to do that is by adding HCl, and that was very, very similar to the HBr mechanism that we've got up here, okay, where you're just turning that into bromo propane or whatever it was. Okay, so the reagent required: hydrogen chloride, HCl gas. What is the type and mechanism of this reaction? Well, you're clearly adding something, you're not substituting it, so you're going from 3 things around a carbon to 4 things, so it's going to be some sort of addition. The other thing is, as we said earlier, this is very, very electron rich, so we need something that likes negative charge, likes electrons, so we need electrophilic. Okay, philic meaning liking electrons, electrophilic addition, so this would be A, as it says there. 1-chloropropane and 2-chloropropane can be converted into compounds containing the nitrile functional group. Under appropriate conditions, 1-chloropropane can be converted into butane nitrile, CH3, CH2, CH2, CHN. What reagent will you need? So I'm going to use skeletal formula here. We've gone from 1-chloropropane to C triple bond N there. Okay, so what have we done? Well, we've clearly swapped a chlorine for a CN group, so we're looking for anything that will provide a CN group. Ammonia, no. Nitric acid, no. Cyanide, yes. Silver nitrate, no. So KCN, and of course what happens here is that your CN group, negative charge on the carbon, okay, very unusual. Carbon is negative in the cyanide ion, that will attack in, kick out the chlorine in probably an SN2 reaction, if I remember my my A-level and undergraduate chemistry. Okay, so we'll swap the cyanide group or the chlorine group for a cyanide group. What is meant by a structural isomer? Well, a structural isomer is when you've got the same atoms, the same number of atoms, the same type of atoms, but they are arranged differently. So an answer that makes reference to the following point: they've got the same molecular formula. Ignore similar, it has to be the same molecular formula, but they have different structural or different displayed formula. Allow a different order arrangement of atoms, so I would have got that mark. Ignore examples. Here, interestingly, it says do not award general formula, because of course they have to have exactly the same formula if they can be structural isomers. Give the displayed formula and the systematic name of the isomer of butane nitrile formed in C2. You must show all the bonds. Okay, so we've got chlorine here, and if I'm showing all the bonds, I've got to show all of the hydrogens. Here, the cyanide, cyano group coming in and kicking out the chlorine. So you are going to have carbon C123N, hydrogen down there, CH. Okay, so you might be tempted to call this something like 2-cyanopropane, but unfortunately this group takes precedence in the naming. So the main chain that we are interested in is this one here, and that is propane nitrile, and we can see therefore off the second carbon, if that's the first one from the cyano group or the nitrile group, 2 there, so it must be 2-methyl propane nitrile, hopefully 2-methyl propane nitrile. Okay, so you could have had methyl propan nitrile. Okay, and there is the bonds there. All bonds must be shown, which I have done. Do not award 2-cyanopropane, as I said there. Absolutely, that's showing you're not understanding that this takes precedence. This is the most important functional group here. Mark 2 dependent on Mark 1 are very near miss. This question is about enthalpy changes. Okay, so something from my half of the course. We've told you again and again to learn these definitions. If you haven't learned these definitions, more fool you. What do we mean by the standard enthalpy change of combustion? It is the enthalpy change when 1 mole of a substance burns completely in excess oxygen. That's only 1 mark here, sometimes it's worth 2, but 1 mole of a substance burning completely or burning in excess oxygen or fully combusting under standard conditions. Okay, it does interesting to say do not award just under standard conditions. Okay, you had to say 100 kilopascals, which is 1 bar, and a stated temperature, but it did allow you to state the temperature, like for example 298 Kelvin. Allow energy released rather than enthalpy. Write the equation including state symbols for the reaction that occurs when the standard enthalpy change of combustion of octane is measured. Okay, and you do need state symbols for these always, even though it hasn't told you, but you do need them. C8H18 liquid, okay, and it even tells you it's liquid, plus some number of O2. Right, well, we've got 8 carbons, so it's going to be 8 CO2 gas, and we've got 18 hydrogen, so it's going to be 9 H2O. Okay, standard conditions. The water is going to be liquid. Okay, that's the standard enthalpy of combustion, forming all chemicals in their standard states. 16 plus another 9 makes 25 oxygens, so 12.5 O2. Okay, it does say burning 1 mole. 1 mole burning, so don't be tempted to double this. Correct species, 1 mark. Balancing and state symbols, another mark. Standard enthalpy change of combustion is -5470. Complete the reaction profile diagram for the combustion of octane. Include labels showing the standard enthalpy change of combustion and the activation energy. Okay, so what do you need to do? Well, firstly, it's exothermic. So therefore, your product must be lower in energy. We're asked to put in the activation energy, so that is from the reactants up to the top. Be careful with these arrows, don't be slapdash. Okay, do show it directly from there to there and label it activation energy, and the enthalpy of combustion, delta HC, is from the reactants to the product, so delta HC standard. How was that marked? 1 mark for a line rising to a maximum then falling to products lower than reactants, and the second mark labelled arrows for the activation energy EA and the enthalpy change of combustion, which touch or almost touch the maximum and be level or almost level with the product and reactant lines. Okay, do not award double-headed arrows, right? Do not award lines with no arrow. Their signs are really important, so please pay attention here. You have to show a single-headed arrow so that you can correctly show the direction of the energy. Activation energy is positive, it takes energy. This reaction is exothermic, so the overall energy change is negative. Enthalpy changes are reactions which can be not measured directly, can be calculated using standard enthalpy changes of combustion. Table shows some of these values. Complete the Hess cycle. Right, so we've got carbon solid and 2H2 gas forming CH4 gas. Right, enthalpy of combustion, burn down. Okay, so we're burning down, so the arrows go away, they form CO2 gas plus 2H2O gas. Okay, so state symbols, correct numbers, but the arrow's going down. We burn down, we build up in formation, but we burn down. Second thing, what do we have? Well, the enthalpy of combustion of carbon is minus 394. The enthalpy of combustion of hydrogen is minus 286, but there's 2 of those, 2 times minus 286. Burning this is minus 890 kilojoules per mole. And we want to know the standard enthalpy change for this reaction. So that is going with this arrow and back up. So it is plus minus 394 plus 2 times minus 286 minus 890. And if you plug that into a calculator, you get an answer of minus 76 kilojoules per mole. So let's see how that was marked. Species and balanced, 1 mark. Arrows pointing downwards, 1 mark. Calculation of delta H reactants and showing, delta H combustion reactants and delta H combustion products, somewhere 1 mark, and final calculation 1 mark, minus 76 kilojoules per mole. Correct answer with no working gets the final 2. Units are not required, but if given must be correct. Ignore significant figures. Here, do not award kilojoules per mole by itself, so i.e. you can't just get 1 mark for the correct units. Next question. Methanol is manufactured from a mixture of carbon monoxide and hydrogen. Give 2 characteristics of all reactions at equilibrium. Right, products equals reactants. No. Do not award the concentration of products and reactants are equal. It's what GCSE students say all the time. It's not true. What is equal, the rate of the forward reaction is equal to the rate of the reverse reaction. That is true. The second characteristics is that the concentration of all components stays constant. They don't have to be equal, but they are unchanging. So you end up with a constant concentration of every species there. Interestingly, it says ignore in a closed system. This is needed at GCSE, but clearly isn't needed here. How does the equilibrium yield of methanol change if the temperature is increased at constant pressure or the pressure increased at constant temperature? So we've got carbon monoxide gas plus 2H2 gas in equilibrium with CH3OH gas. Right, first thing to notice, there are 3 gas molecules or moles, and there's only 1 here. So therefore, if we increase pressure, then the equilibrium will want to move to decrease the pressure. It will move to the right. So if we increase pressure, the system wants to decrease the pressure. It can do that by moving to the right, so more methanol. What about temperature? Well, if we increase the temperature, the reaction wants to cool down again. How can it do that? It can go in the endothermic direction to take in that extra heat energy that we supplied. So if we increase temperature, it wants to go in the endothermic direction, suck in that extra energy, thermal energy we supplied. It will go that way, so there will be less methanol. And that corresponds to a decrease when the temperature is increased, but an increase when the pressure is increased. In other words, B. Explain your answer. I've pretty much done it. An explanation which makes reference to the following points. A rise in temperature causes the equilibrium to shift in the endothermic direction, and therefore it will move to the left. Second thing is that higher pressure, it will shift to the side with fewer gas molecules. And the second one there. You didn't do this question, ignore that. This question is about compounds with the molecular formula C4H8O. What is the percentage by mass of each element in that? Okay, so C4H8O, the total mass of that is 12 times 4 plus 8 plus 16, which equals 48 plus 8 plus 16 equals 72, of which 48 over 72 is carbon, so that is 66.67%. So instantly A is right. There we go. Finally, 3 different compounds have the molecular formula C4H8O. Right, they've all got IR absorptions at about 3,500 per centimetre. So we look at our Databook, GCSE Chemistry Databook, and we can see around 3,500. What are we looking at? OH, there we go. OH stretching vibrations. So they've all got an OH group in them. Okay, what else do we have? Well, we know that A and B have 1650. So A and B have something at 1650. What is that they have? 1650. Oh yeah, there you go. An isolated alkene. So they've got a C double bond C, which they don't. What other information are we given? Only A has a branched chain, B is the E isomer of a pair of stereoisomers. Okay, well, let's have a think about the molecular formula itself, C4H8O. If we had 1, 2, 3, 4, and an OH group, we would expect 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. The fact we've only got 8 hydrogens means that we are missing 2. That means there is either one double bond, which we know that there is for A and B, but in the case of C, how can we get rid of 2 hydrogens? The answer is that there is a ring. So C must have some sort of ring structure. So the most obvious thing to try with C is, if the 4 carbons are in a ring with an OH group, does that work? 1, 2, 3, 4, 5, 6, 7, 8. There's no counter indications, So that absolutely fits all the information we have for C. A has a branched carbon chain. Okay, well, we've only got 4 carbons here, so that is potentially the only option we have here really is 4 carbons like that. So now we just need to stick on an OH group, OH up here. So 1, 2, 3, 4, 5, 6, 7, 8. That fits all the information about A. It has a branched carbon chain. It's got the OH group. It's got an isolated C double bond C. You could have put the OH group on this side attached to that carbon, but I was trying to keep the OH group away from the CC if at all possible. And finally, B, we're told that there is an E isomer of a pair of stereoisomers. So what can that mean? Well, E means on opposite sides, doesn't it? E is a cross, so CH3 here, H3C here, hydrogen, hydrogen, and again that fits with all the data for B. There are other options, so are there other options? No, there aren't. If you've got a pair of stereoisomers, then it's not possible to do this because there's no other isomer possible. Isomer possible, so it can't be that. So let's have a look at how that was actually scored. We've got one of these, number of indicative marking points, number of points awarded. And then logic 210. So indicative point 1, IR data shows that they all have an OH group and A and B have a CC group. That's 1 marking point, 1 indicative point. So that's the first one there. 2, B must have 2 different groups attached to each carbon of a double bond. We had that in the final structure. IP3, C has no double bond, so it must be cyclic. I mentioned that, so I definitely get that. A is, yeah, this is what we had. We had the double bond, we had the branched chain, and then we had the OH group, so I definitely got that. B must have the carbon. Oh, yeah, of course. I am stupid. I forgot the OH group for that, so I would not have got that mark due to my own stupidity because I forgot that I needed an OH group, so I wouldn't have got that. And 6, C is that cyclic with the OH, so I would have got that. For the second one, allow a discussion of priority groups, allow that the double bond must be in the middle. So I guess implicitly I did get that, didn't I, in my answer. So probably I got that implicitly. So I would have got that one. So how would I have scored that? I reckon I was partially structured in my answer, so I got 1 mark and I got 5 of the indicative points, so I would have got 3 of the marking points, so therefore I would have got 4 out of 6 for that because I didn't specifically explain everything, and I forgot the OH group on here. Okay, I hope that that was helpful. I'll just show you all the caveats there that you can just read through yourself. Now what you need to do is, that's the end of your 3rd lesson. Just make sure you know where you lost the marks, why you lost the marks, and if there's any areas you need to revise in far more detail. Because remember, next week we're moving on to year 13 material. The other thing is the final lesson of the week. You need to go to that 2019 paper 2 and complete the remaining questions as you have done for paper 1. Other than that, I'll see you next week. Thank you.